Hello everyone, this is Vijetha, Associate Professor in the Department of ECE from MLR Institute of Technology. Today I would like to talk on differentiator which can be generated by using a IC741 from linear and digital integrated circuits. So these are the topics which I want to cover in this video. How an IC741 can be used as a differentiator circuit, and what are the limitations of a differentiator, what are the applications of differentiator, and why we are going with the practical differentiator, what are the disadvantages of an ideal differentiator and why we are going with the practical differentiators. So this is a circuit which is used as a differentiator. Op-amp consisting of a negative terminal and a positive input terminal. This is called as an inverting input terminal and this is called as a non-inverting terminal. This is how you can arrange a capacitor and resistor to work this IC741 as a differentiator. A circuit is said to be a differentiator when its output voltage is differentiation of your input voltage. And this operation is very useful to find the rate at which signal varies with respect to time. So, from this circuit, we have to derive V0 is equals to some constant into dVi by dt. That is, whenever the input voltage is related with output voltage as a V0 as differentiation of input voltage. That means from this circuit we need to prove V0 is equals to some proportionality constant into dVi by dt. So we need to get the relation between V0 and Vi as V0 is equals to dVi by dt. So here, as by using a virtual ground concept, we can say that, or we can say as the gain of this amplifier is very high, so the voltage across VB, which is equals to voltage across VA, will be equals to 0. So now, by applying a KCL across this point, we can write the equation as IC is equals to IB plus IF, this small IC, that is current entering into the terminal. As gain is high, IA is equals to IB is equals to 0. IA is equals to IB is equals to 0. So from this we can write the current across the capacitor will be equals to the feedback current IF. We can write IC as the current across the capacitor can be given as IC is given as D into differentiation of Vi minus Va divided by dt into this C1, and the current across the resistor IF is given as IF is equals to Va minus V0 divided by RF, Va minus V0 divided by RF. As gain is high, VB is equals to VA is equals to 0. So, you can write IC as dVi by dt into C1 and IF is given as minus V0 by RF. But by applying a KCL at node A, that is at inverting terminal of an op-amp, we got the current across the capacitor, which is II, is equals to the feedback current. So the current across the capacitor, we got it as C1 into dVi by dt, and the feedback current, we got it as V0 divided by RF, feedback resistor. From this we can write minus V0 by RF, we got it as minus V0 by RF. So we can write V0 is equals to minus RF into C1 dVi by dt. So it is proved that V0 is some proportional with differentiation of your input voltage with respect to time. If you want to represent this in a frequency domain, you can write it as V0 of S is equals to minus RF C1 into S into d Vi of S. This is how you can write in a frequency domain. Now, for this ideal differentiator, what are the limitations of this ideal differentiator? The differentiator circuit is more susceptible to noise compared with the integrator circuit. The input noise fluctuations will generate large noise signal at the output because of this differentiation. Because of the differentiation of your input signal, that produces a large noise signal at the output side, which introduces a poor signal to noise ratio, and this can be minimized by placing a resistor in series with the input capacitor. And the modified circuit differentiates only a low frequency signals with a high frequency gain. And in differentiator circuit, limitations due to noise stability and input impedance, a small capacitor has been placed with RF will provide a high frequency gain. So, as the frequency increases, the differentiator increases due to the gain of the differentiator increases due to reduction of input impedance. Therefore, at high frequencies, the differentiator becomes unstable, and this makes the circuit very sensitive towards the noise, and it affects the stability also. The circuit which is showing here is a practical differentiator circuit. R1 is added to a series with the capacitor C1 to reduce the signal to noise ratio effect, and the CF, the feedback capacitance, is added to RF to maintain the stability of the circuit. Here, by applying a KCL across the node A, you can write IC is equals to IF1 plus IF1 plus IF2. IC is the current across this R1 series with the capacitor C1, and IF2 is the current across the CF. IF1 is the current across the feedback resistor RF. This IC can be given as the current across this series network is given as VI minus VA divided by Z1. As we know that VB is equals to VA is equals to 0 because of the gain, high gain, you can write IC is equals to VI by Z1, where Z1 is R1 is series with the capacitor C1, which you can write as R1 plus S into C1. So, Z1 is given as R1 SC1 plus 1 divided by SC1. So, the current across the capacitor can be given as IC is given as VI into SC1 divided by 1 plus R1 C1 into S. So, let this be equation 1, let this be equation 2. Now, we will find out what is IF1 and IF2. See, this IF1 can be given as this VA minus V0 divided by RF. So, you can directly take VA as 0 because of the high gain. You can write IF1 is equals to minus V0 by RF. Now, this IF2 is given as VA minus V0, that is CF into this will write. This IF2 can be given as this IF2 is the current across the capacitor CF, which you can write it as CF into dVA minus V0 divided by dt, as VA is equals to 0. IF2 can be given as minus CF into dV0 by dt, and IF1 is given as minus V0 divided by RF. And IC can be given as voltage across the capacitor is given as VI into SC1 divided by 1 plus R1 C1 into S. Now, if you can write this IF2 in a frequency domain, you can write this IF2 as minus S into CF into V0 of S. Now, if you can substitute these three, that is IF1 and IF2 and IC in equation 1, that is IC is equals to IF1 plus IF2, you can rewrite this expression as VI into SC1 divided by 1 plus R1 C1 S is equals to minus V0 V naught divided by, that is V naught of, if we are writing in terms of frequency domain, V naught of S divided by RF minus S into CF into V naught of S. Let this also be Vi of S as I am writing in terms of frequency domain. So now this equation can be given as Vi of S into C1 into S divided by 1 plus R1 C1 S is given as minus V naught of S. If you can take common, you can write it as 1 plus RF plus SCF, which you can write as 1 plus S into CF RF divided by RF. So if you want to write in terms of V naught of S, you can write this as minus Vi of S into C1 RF divided by 1 plus R1 C1 into S into 1 plus S into CF RF. Let us assume that R1 C1 is equals to RF CF. Then this equation can be given as V naught of S is equals to minus Vi of S into SC1 into RF divided by 1 plus 1 C1 into S whole square. If you are assuming this is very less value, you can write this equation V naught of S is equals to minus Vi of S into S C1 RF. If you can write this equation into a time domain, you can write it as V naught of T is equals to minus RF C1 into dVi by dt divided by dt, dVi of T divided by dt. So this is giving a proportionality constant between output voltage as a differentiation of input voltage. So V naught is proportional to dVi by dt. If you want to know the frequency analysis from this expression, that is V naught of S is equals to, let us substitute S is equals to j omega. So you can rewrite this expression as V naught of j omega is equals to, or you can write, now we got output voltage V naught of S is equals to Vi of S into S R1 CF divided by 1 plus S R1 C1 whole square. So if you want to find out the gain, you can write it as V naught, magnitude of V naught of S by Vi of S, which you can given as S into R1 CF divided by 1 plus S R1 C1 whole square. Now if you can substitute S is equals to j omega, you can write V naught of j omega divided by Vi of j omega as j omega into R1 CF divided by 1 plus j omega into R1 C1 whole square. As we know that omega is equals to 2 pi f, you can write this as magnitude of V naught of j omega divided by Vi of j omega is equals to j into 2 pi f into R1 C1 divided by 1 plus j into 2 pi f into R1 C1. Let us assume that 2 pi R1 C1 as 1 by Fa and 2 pi R1 C1 as 1 by Fb. So now from this you can write the gain as j into f by Fa divided by 1 plus j into f by Fb. The magnitude of gain you can write it as f by Fa divided by root over 1 plus. So this is where I haven't applied a magnitude. But now if I have applied a magnitude, so we got A is equals to j f by Fa divided by 1 plus j f by Fb. So magnitude of gain can be given as now f by Fa divided by root over 1 plus f by Fb whole, 1 plus f by Fb whole square, that is f by Fb square. So the gain is given as f by Fa root over 1 plus f by Fb whole square. So, and coming to applications, the differentiator circuit can be used for wave shaping, used as a wave shaping circuit, and it also used to convert triangular wave to a square wave. It is also called as a triangular to square wave converter. So in this video, first we have derived the V0 of t as minus R1 CF into dV0 by dt divided by dt for an ideal differentiator. Then, as the ideal differentiator is providing a noise, more noise, and providing a poor signal to noise ratio, and as it is not stable, we have gone through a practical differentiator by placing a R1, that is input resistor, series with C1 and the feedback capacitor parallel to a feedback resistor, and we derived V0 of t is equals to minus R1 CF by dV0 by dt into dt. And now coming to applications, this circuit is used to provide a square wave by giving a triangular wave as an input, and also used as a wave shaping circuit. So we got a magnitude of gain as f by fa divided by root over 1 plus f by fp whole square. Now coming to applications, this is work as a wave shaping circuit, and also it converts a triangular wave to a square wave. So in this video, we have discussed about an ideal differentiator which is producing output voltage V0 of t is equals to minus RF C1 into dVi by dt into dt, as this is providing a poor signal to noise ratio and it is providing a more noise, and as it is not stable, a input resistor is added in series with C1, and by placing a feedback capacitor parallel with a feedback resistor, we generated a practical differentiator which provides an output as V0 of t is equals to minus R1 CF into dVi by dt divided by dt, and the gain as f by fa divided by 1 root over 1 plus f by fb whole square. And coming to applications, this is used to generate a waveform generator and used to convert a triangular wave to a square wave. Thank you.